Let us discuss effect of dielectric on capacitance of a capacitor. Here we consider a parallel plate capacitor. Effect of dielectric on capacitance of a parallel plate capacitor. Consider a parallel plate capacitor having each plate area A and separation between its plates D. Let Q be the charge on the capacitor. That is, one plate is having plus Q charge and other plate minus Q charge. When there is vacuum between the plates, this is parallel plate capacitor. Say plate 1, it has plus Q charge and plate 2, it has minus Q charge. Each plate area is A. Say here surface charge density is plus sigma, and on this plate surface charge density it is minus sigma. Here sigma is equal to Q upon A. When there is vacuum between the plates, electric field at a point, it is directed left to right. Plate 1, that is left plate, its electric field, it is pointing left to right. Plate 2, that is right plate, its electric field at this point also points left to right. Magnitude of net electric field between the plates of the capacitor E naught So magnitude of electric field due to positive plate, it is sigma upon 2 epsilon naught. You know, if there is a non-conducting plate with surface charge density sigma, then electric field near it is sigma upon 2 epsilon naught. Here, this plate, it is having charge on one side. It behaves like a non-conducting plate, so its electric field, it is sigma upon 2 epsilon naught at this point, directed left to right. Due to this negative plate, electric field, it is also directed left to right, and magnitude of electric field due to negative plate at this point, it is also sigma upon 2 epsilon naught. So net field, it is sigma upon epsilon naught. Sigma is equal to Q upon A, so it becomes Q upon A epsilon naught. Potential difference. V naught is equal to, since electric field is uniform between the plates, so potential difference, it is magnitude of electric field multiplied distance between the plates. You know, in uniform electric field, potential difference, absolute value, it is equal to magnitude of electric field multiplied the distance. So V naught is equal to U naught D. E naught, it is Q upon A epsilon naught. From here, you have Q upon V naught is equal to A epsilon naught upon D. Q is the charge on capacitor. One plate is having plus Q charge, other minus Q charge. So you know, ratio charge on capacitor to potential difference between the plates. Q upon V naught, it is the capacitance of the capacitor. Since there is vacuum, so this capacitance we denote by C naught. So C naught is equal to A epsilon naught upon D. Now let us see what happens when a dielectric is filled fully in the space between the capacitor plates. When a dielectric of dielectric constant K is filled completely between the plates of the capacitor. So see, this is capacitor with plate area A, separation between the plates D. First plate is having plus Q charge. Surface charge density plus sigma. Second plate, it is having minus Q charge. Surface charge density minus sigma. And a dielectric, it is filled in the space between the plates. And this dielectric has dielectric constant K. So you know, when a dielectric it is placed in an external electric field, then it gets polarized. Surface charge densities are induced on sides of the dielectric, that is, there is net dipole moment developed inside dielectric. And you also know electric field is reduced inside dielectric because external electric field it is present inside dielectric and an internal electric field it is developed in opposite direction of external field. So net electric field it is reduced inside dielectric to E. Say at this point, net field it is E in presence of dielectric. This field it points in the direction of the external field and its magnitude is less than external electric field. For linear dielectrics, net electric field magnitude it is external electric field magnitude divided by a constant called dielectric constant of the dielectric. And you have seen E naught, it is Q upon A epsilon naught. So potential difference between capacitor plates in presence of dielectric V is equal to E into D. Since in presence of dielectric, net field between capacitor plates at each point it is E. This electric field is uniform. We have already neglected fringing effect of electric field, that is, we have considered plates large and distance between the plates small. When capacitor plates are large and they are close, then fringing of electric field at the edges can be neglected and we can assume electric field to be uniform. So here electric field is uniform, its magnitude is E, potential difference between the plates V is equal to E into D. E we have obtained, so it becomes Q upon A epsilon naught K multiplied by D. And from here you can have Q upon V, it is equal to K A epsilon naught upon D. And you can see when dielectric is present, then capacitor each plate it is having charge magnitude Q, potential difference between capacitor plates it is V. This ratio Q upon V, it is capacitance of the capacitor in presence of dielectric. So C is equal to and you have seen A epsilon naught upon D, it is the capacitance when there were no medium between plates, that is in presence of vacuum. This means this is equal to K multiplied C naught. So you can see in presence of dielectric capacitance, it becomes K A epsilon naught upon D, which is equal to K times capacitance of the capacitor when there were vacuum or air between the plates. That is, in presence of dielectric capacitance, it becomes K times the capacitance of the capacitor in presence of vacuum or air. And you know, dielectric constant of a dielectric, it is always greater than 1. So, in presence of dielectric, capacitance of the capacitor increases. So you have in presence of dielectric capacitance C, it is equal to K A epsilon naught upon D, that is C is equal to K times C naught. Now let us see what happens when dielectric is partially filled between capacitor plates. Let us consider capacitance of the capacitor when dielectric is partially filled between capacitor plates. Dielectric partially filled between capacitor plates. Consider a parallel plate capacitor having each plate area A and separation between its plates D. Let plus Q and minus Q be charge on capacitor plates. And a dielectric slab of thickness T is filled between capacitor plates. Plate area is A and area of sides of dielectric, it is also a dielectric slab of thickness T, it is filled between capacitor plates. Distance between capacitor plates, it is D. Plate area is A. And dielectric constant of the dielectric is K. So here you can see there are three regions between capacitor plates. In this region, electric field, it is directed left to right, and its magnitude, it is E naught. Inside dielectric, electric field, it is reduced to E, and it is also directed left to right. And here in this region, electric field, it is directed left to right, having magnitude E naught. In first region there is vacuum, in second region we have dielectric, in third region we have vacuum. In vacuum, electric field, it is E naught, and in dielectric, electric field is E. And you know E is equal to E naught upon K. Now let us consider points. So this point is P, this is Q, this is R, and this point is S. Potential difference between capacitor plates. V, it is equal to Vp minus Vs. First plate, that is plate which is having positive charge, its potential is Vp, and second plate, the plate which is having negative charge, say its potential is Vs. So Vp minus Vs, it is the potential difference between capacitor plates. So V is equal to Vp minus Vs, and we can write like this: Vp minus Vq plus Vq minus Vr plus Vr minus Vs. And you can see Vp minus Vq, this is equal to E naught, and say this distance, it is x. So Vp minus Vq, it is E naught multiplied x. Vq minus Vr, it is E multiplied T, plus Vr minus Vs, it is E naught multiplied, you can see this distance between points R and S, it is equal to D minus T plus X. Here we have used the relation potential difference in case of uniform electric field is equal to magnitude of electric field multiplied by the distance between the points. So this becomes E naught x plus E is equal to E naught upon K plus E naught we can take common, and it is x plus t upon k plus d minus t minus x. X cancels out, so it is equal to E naught in bracket d minus t plus t upon k. We have V is equal to E naught d minus t, you can take common, 1 minus 1 upon k. And E naught you know, E naught it is equal to q upon a epsilon naught. Here E naught, this is the electric field at this point in vacuum. So electric field due to positive plate, it is, you know, q upon 2 a epsilon naught plus electric field due to negative plate, it is q upon 2 a epsilon naught. So this is equal to q upon a epsilon naught. So E naught is q upon a epsilon naught, d we can take common, and here we have 1 minus t upon d in bracket 1 minus 1 upon k. From here, q upon v is equal to q upon v is equal to a epsilon naught upon d, in denominator 1 minus t upon d, 1 minus 1 upon k. And you know q upon v, it is the capacitance of the capacitor. So C is equal to a epsilon naught upon d divided by 1 minus t upon d, 1 minus 1 upon k. So you have C is equal to a epsilon naught upon d, it is the capacitance in presence of vacuum between the plates, divided by 1 minus t upon d, 1 minus 1 upon k. So this is the expression for capacitance of the capacitor when a dielectric of dielectric constant K of thickness T, it is filled partially between capacitor plates. Here you can see the denominator, it is 1 minus t upon d in bracket 1 minus 1 upon k, and you know k, it is always greater than 1. So 1 upon k, it is less than 1. Quantity in this bracket 1 minus 1 upon k, it is positive and it is less than 1. T, this is less than d. So denominator, it is less than 1 and it is positive. So this implies C is greater than C naught. Means in presence of dielectric, capacitance of capacitor increases. And you can see, if dielectric is completely filled between capacitor plates, that is T is equal to D. If dielectric is fully filled between the plates, then T is equal to D. So from the simulation, we have C is equal to C naught upon 1 minus D upon D, 1 minus 1 upon K. And it is equal to C naught 1 minus D cancel out, 1 minus 1 plus 1 upon K. So it becomes K times C naught. That is C is equal to K times C naught. So when dielectric it is completely filled between capacitor plates, then capacitance it becomes K times the capacitance of the capacitor in presence of vacuum or air.